You all set? Yes. Nervous?
That'll calm me down. Guess we might as well start.
Just want to preface, Andy is going to give us a little bit of a lesson on some chemistry stuff as part of his senior project. He's videotaping it, and his dad's here to help him, and he's, of course, my guy this semester for his senior project, which some of you, of course, are involved in. Some of you will. All the rest of you will be eventually. So give him your attention. He's going to take up about 20, 25, 30 minutes of our time this morning. Okay? Thank you. Andy Church.
Let me start by asking, what do you guys know about nuclear power so far? Like, just right off the top of your head. What's some of the stuff you've heard?
It's apparently more efficient than regular sources of power.
That is true. They use it for about 20% nationwide as the power source. About North Carolina, it's about 50% of the power generated. Anybody else anything about it? Okay, that's cool too. I did my PowerPoint on the fuel fabrication. They have to enrich the uranium to be able to use in the power plant, and researched the equations for that to operate the PowerPoint. First thing they have to do is they have to dig up the uranium somewhere. Australia is where they do a lot of it. They use a leach mining where they dig up the ore and leach the uranium out of it using an acid. Whenever it comes out of the ground, it's U3O8, and they also call it yellow cake. Why they call it yellow cake? Because it looks just like cake. It really does. They have to purify it to where they can start enriching it to make it usable in the power unit. They have to start the purification. The top equation is the one they use in other places around the world, but in the United Kingdom, the United States, France, and Canada, they use the one that's in red at the bottom. They do not use ammonium in the purification of uranium. They need to make uranyl nitrate to where they can increase the isotopes of uranium-238 to uranium-235. Uranium-235 is the fissile isotope that they're looking to gain.
We're going to be learning about equations here today.
They have to continue to convert the uranyl nitrate into uranium trioxide. I'm not exactly sure why they stop at uranium trioxide in this equation. That I could not find. The next equation that's on there, they go ahead and convert it to uranium dioxide, which is the ceramic form that they use to make the power fuel assemblies. They just take and add hydrogen to where the hydrogen will bond with the extra oxygen and make water and the uranium dioxide. They then add fluorine to it so they can transport it as a gas form. They start out by making it UF4, and then they add more fluorine to it to get a continued bond. The UF6 is a lot more stable than UF4, that's why they continue to add fluorine to it. Then they have to start enriching the uranium. The the uranium-235 isotope is the one that they look to gain. Whenever they dig up uranium, the isotopes are about 97% uranium-238, which is not as usable, and about 3% uranium-235. They look to change those percentages and make the uranium-235 a lot higher. Like I said, there's the percentages. I was a little off, but it's about the same. The uranium-235 is the one they want to gain because whenever a neutron is fired into it, it becomes unstable at uranium-236 and decays to krypton and barium and releases 3 neutrons. They have 3 different types of enrichment. Laser enrichment is the newest one, and General Electric will not provide me information about it because they are keeping it secret at this point. Gaseous diffusion is the one that General Electric uses at their Wilmington plant to enrich the uranium to make it usable. There's also a centrifuge method that they use to enrich the uranium. The gaseous diffusion is used most though. The gaseous diffusion, they take and pass the uranium through a filter, and the filter is fine enough to pick up the difference in the atomic weight, the uranium-238 versus the uranium-235. The filter will stop the uranium-238 and let the uranium-235 pass on through. That's shown in the next slide on the image over to the side there. Then they take and form it into ceramic pellets and put it in the fuel assembly. That's later in the PowerPoint. The centrifuge works on the same method. They take and put the gaseous uranium hexafluoride, the UF6, into the center of the centrifuge, and they spin it. The heavier isotope moves to the outside. They then scoop off the uranium-235 out of the middle. Then the laser enrichment, like I said, General Electric will not provide me information on it. The image there is about as good as I can show how they do it. They shine a laser onto the stream of uranium hexafluoride, and it excites the uranium-235 more than it does the uranium-238. Then the uranium-235 is pulled off. Then they start building a fuel assembly. They take the ceramic pellets that they form out of the enrichment and slide those down into zirconium rods and put them in a fuel assembly. They typically use 4% uranium-235 to uranium-238, and 96% uranium-238. That's the one they found at NC State while I was down there. They said that that was their percentage. A power reactor uses a little more uranium-235, typically like 5% uranium-235. The Navy, however, uses like 99% uranium-235 in their submarines. Then they take and put together the fuel assembly like over in the top right corner. The pellet goes into the fuel rod, and the fuel rod goes into assembly. The assembly then is put in the core of the reactor, and there's several fuel assemblies in one core. That one is a fairly large core. It's used for generating electric power. I would say there's 150 or so fuel assemblies in that core. I didn't count because you can't tell. They put several of those in there just because they needed to sustain a chain reaction and build up the temperature hot enough to produce electricity. There's the reaction itself, the fission reaction. They fire a neutron into the uranium-235, and it becomes unstable at uranium-236, and then breaks down to krypton and barium, 141 and 92, and then releases 3 more neutrons, which bombard more uranium-235, and then it continues to decay, creating a chain reaction. Then they use the heat that is formed from that chain reaction to boil water in a steam generator, and then pass it across the turbine, and that generates the electricity that we use. And that's just the acknowledgments to the people that gave me information. Alright, that's it. Thank you. I didn't mean to make you operate my PowerPoint.
Oh, no, that's fine. I can hit the buttons. if we have time, I hope to get to nuclear chemistry. In the past, we have not had time. Just have to see. And of course, the decay of uranium